this video is going to introduce the trinomial probability distribution. The where you'll see this in the book is beginning with example 4.1-7 and continuing through to the end of the section with 4.1-9. We're going to start by reminding ourselves about the binomial distribution. Remember that this distribution is useful when we have a fixed number of trials, which we call n. Each trial has two possible outcomes, success or failure. The trials are independent of each other with the same probability of success, which we call p for each trial. And in that case, when we consider the random variable x is the number of successes out of the n trials, we said that x has a binomial distribution characterized by the parameters n and p. Now we're going to consider what if instead of just two possible outcomes, there are three possible outcomes. In this case, we'll be able to use a trinomial distribution. The trinomial distribution is similar to a binomial in that there's a fixed number of trials n. In this case, instead of two possible outcomes, there are three possible outcomes for each trial. But similar to the binomial, the trinomial has trials that are independent of each other, and where the probability that each outcome will occur, each of the three outcomes, is going to stay the same for all of the trials. Here's an example. We have a large pool of insured drivers that are classified into three risk groups: low risk, which will have 60% of all drivers, medium risk, which is 25% of all drivers, and high risk, which is 15% of all drivers. Suppose that we randomly select n equals 10 total drivers from this large pool. We're going to let x equal the number out of the 10 drivers who are low-risk drivers. Y is going to be the number of the 10 drivers who are medium-risk drivers. And z is the number out of the 10 drivers who are high-risk drivers. Note that because we have a total of 10 drivers, we know that z has to be equal to 10 minus x minus y. So when we're talking about the distribution of these variables, we can focus only on the distribution of x and y. If we know the values of x and y, then we can figure out the third value, z, from that. So to start thinking about what the probability mass function for x and y would look like, I'm going to start by looking at one possible outcome of selecting 10 drivers. So we might just happen to have our 10 drivers selected, and the first one might be a high risk, then a low, another low risk, a medium risk, a low risk, then a medium risk, then a high risk, then a low risk, then a medium risk. This is just one of many possible outcomes. We can see that x, the number of low risk drivers out of the 10, is 5. Y, the number of medium risk drivers out of the 10, is 3. Now we know that z, the number of high risk, is going to be the 10 total minus the 5 low minus the 3 medium, gives us 2. And sure enough, if we look at our outcome, we can see there are in fact 2 high risk drivers here. Now let's consider finding the probability that we have x equals 5 low-risk drivers and y equals 3 medium-risk drivers when we randomly select 10 drivers. This is going to be our joint probability f of 5, 3. Now, the 60% of the drivers were low-risk drivers. So we know that the chance that we would choose 5 low-risk drivers, we're going to be looking at, because we have independent trials, we can multiply our probabilities. So we're going to have our 0.6, which is the probability of a low-risk driver, 0.60. We're going to have 5 of those multiplied by each other. We are also going to have, we had in total, in the whole pool, there were 25% medium-risk drivers. So 0.25 is the probability that each individual driver chosen would be medium risk. That happened 3 times, so we'll write that to the third power. And the chance of being high risk was 1 minus the 0.6 minus 0.25 gave us the 0.15 was the proportion of high risk drivers. And since there were 2 of those, we'd have raised to the second power. Now, if we did this calculation, it would give us the probability that we would see exactly this outcome, or exactly any one particular outcome that would have these numbers. But in order to find the total probability that we'd have 5 low-risk drivers and 3 medium-risk drivers, we have to consider how many ways we could have those numbers occurring. And we're going to go back to what we learned in our counting methods, where we said, okay, well, how many distinguishable permutations of these highs and lows are there? And there are 10 factorial divided by 5 factorial times 3 factorial times 2 factorial distinguishable permutations. So this is going to be our joint probability that x is equal to 5 and y is equal to 3. So we can generalize this. So in general, the joint probability mass function of x and y is going to be the number of ways that we could have exactly x low-risk drivers, y medium-risk drivers, and 10 minus x minus y high-risk drivers, times the probability of an individual being low risk raised to the power of the number of low risk, times the probability of medium risk raised to the power of the number of medium risk drivers we have out of the 10, and then multiplied by the probability that an individual driver chosen is high risk raised to the power that indicates the number out of our 10 drivers who are high risk. So that's our sort of general form for the joint probability mass function in this particular case. Now note that x can take any value from 0 up to 10. We could have up to 10 low-risk drivers chosen randomly. Y could take any value from 0 medium risk up to 10 medium risk drivers. But we have the restriction that since we have a total of 10 drivers, we couldn't have x plus y, the total number of low and medium risk drivers, be more than 10. So that's our support is indicated by those bounds. Now if we want to generalize to a sort of situation where we can use this in other examples, if n is the number of trials that we have, P sub x is the probability of the first outcome occurring on an individual trial. Probability P sub y is the probability that the second outcome would occur on an individual trial. Then 1 minus the P sub x minus P sub y would be the probability that the third outcome would occur on an individual trial. Capital X is the random variable, which is equal to the number of times the first outcome occurs out of the n trials. And capital Y is the number of times that the second outcome occurs in the n trials. Then the joint probability mass function for x and y is given by the formula n factorial divided by x factorial times y factorial times n minus x minus y factorial. That's telling us how many ways, distinguishable ways, we could have little x outcome 1 occur and little y outcome 2 occur. We multiply that by p sub x raised to the x power times p sub y raised to the y power times 1 minus p sub x minus p sub y raised to the n minus x minus y power. And the support, as I have here, is that it's the set of all xy pairs such that x is between 0 and n, an integer, y is an integer between 0 and n, and x plus y has to be less than or equal to n. Let's talk then about the marginal distribution of x. When we're interested in the marginal distribution of x, all we're interested in now is the number of the first outcome that occur. We don't care how many times the second outcome occurs, only whether or not the first outcome occurs. So what we can do here is we can lump outcomes 2 and 3 together, which means that we now have 2 possible outcomes. The first outcome occurs would be one of the outcomes, and not the first outcome occurring would be the second outcome, which means that now the marginal distribution of x is binomial. We have 2 possible outcomes. So the marginal distribution of x is going to have the probability mass function given by the binomial distribution with p equal to our p sub x, and the support will be the integer values from 0 up to n. Using the same logic, we can see that the marginal distribution of y is also a binomial distribution parameterized by n, the number of trials, and p sub y, the probability that outcome 2 will occur on an individual trial. So an important thing to remember when we're working with trinomial distributions is that the marginal distributions of x and y will always be binomial distributions. The last thing I want to think about is whether x and y are independent. If we look at the joint probability mass function, we can see that it is in fact not equal to the product of the 2 marginal distribution functions, which means that, that x and y are dependent. And this could also be shown by noting that the support of x and y is not rectangular, because remember that although x can take on values from 0 up to n, and y can take on values from 0 up to n, they can't add up to more than n. So if x is equal to n, then the probability that y is equal to n would have to be equal to 0. So clearly these are dependent random variables. Even though the trials themselves are independent from each other, the number of outcomes that occur of each type are dependent. I hope this helps you get started with the trinomial distribution. Have a good day.